In this video, we're going to consider how to factor quadratic and cubic expressions. So let's review a little bit of a vocabulary. So when we say the word terms, they're separated by a plus or minus, by addition or subtraction. A constant is a number that is not multiplied with any variable, and therefore that term cannot change, and we call it a constant. While a coefficient is the number that is multiplied with the variable and is usually written in front of the variable. A lead coefficient is a special type of coefficient, and it is the number multiplied with the variable that has the highest coefficient. So make sure you're familiar with these terms, as we will be using them throughout the video. So let's consider how to factor out the greatest common factor. Now, factors are just what we multiply together to get our terms. So for example, when we consider 9w to the third, if we were to break it down to prime factors, and remember prime just means it cannot be divided by anything other than itself in 1. So if we were to break this term down, we would say 9 is just 3 times 3 and 3 w's. So all of those are your prime factors, versus for 45 we would have 3 times 3 times 5 and 2 w's. So if we consider these two terms and their prime factors, we can consider what is their greatest common factors. So what's the greatest factors we could pull out from both of these terms? So we have 2 3's in each of these terms, which would give us a 9, and we also have 2 w's, which would give us a w squared. So we would say our greatest common factor is 9w squared. And then when you factor out the greatest common factor, you need to write the leftover factors from each term in a parentheses. So from the first term we have this w minus, and in the second term we have the 5 left over. So I'm going to call those the leftovers, that's not a mathematical term. And the way you could always double check your work would be to always multiply the greatest common factor back with each of the terms and make sure it gives you the original problem. Now, you do not have to do this extra step if you can find the greatest common factor in your head, but if you're ever stuck, feel free to write it down to the prime factors. Now let's consider this second problem. Well, the first thing, before you ever start factoring any type of problem, the most important thing is to write your terms from highest exponent to lowest exponent for your variables. So looking at this problem, I'm going to rewrite it so that I have negative 7x squared plus 14. Now we can consider what's the greatest common factor. However, notice that this first term, my lead coefficient, is now negative. When your lead coefficient starts with a negative, for good practices moving forward in our next units, we always want to include in our greatest common factor, factoring out a negative when the lead coefficient is negative. So even if we didn't have any other lead coefficient, we always will factor out a negative from the lead coefficient. But in this case, besides the negative, we will also have a 7 that both of these terms have as their greatest common factor. Now, if I want to factor out a negative 7, remember, to check if I factored correctly, I just need to multiply back to each of the terms. So to find out what's left over in the parentheses, I can just divide each of the terms by my greatest common factor. So in this case, if I divide negative 7x squared, I'm left over with x squared, and 14 divided by negative 7 is negative 2. Always double check by distributing and multiplying back the greatest common factor to what you wrote in the parentheses. And keep in mind, we're going to now take a look at other types of factoring, but a couple of rules to keep in mind is, first, always make sure your degrees for your variable are from highest to lowest, and that if there's a negative, factor out a negative if there is one in the leading coefficient, as well as check for a greatest common factor before employing any of these following methods. When you are given an expression with 4 terms, the first thing you should check is if you can factor by grouping. The way we do this is by first remember to check for the GCF in all 4 terms. If there's no greatest common factor, then you're basically going to take those 4 terms and divide it up into the problem into 2 terms at a time. And you're going to factor out the greatest common factor from the first 2 terms. And then you're going to factor out the greatest common factor from the last 2 terms. So looking at this example, we see that we have in the first 2 terms, the greatest common factor is an x squared, and we are left over with x minus 2. When looking at the last 2 terms, I'm pretending that this positive 16 is a lead coefficient, and since it's positive, I'm not going to have to factor out a negative, so I'm just going to put positive there. And the greatest common factor between 16x and negative 32 is just positive 16, and I am left over with x minus 2. Now, you know that you can factor by grouping and that you've done this correctly if your 2 parentheses match, which they do in this case. So the way we're going to continue this problem and finish it off is by considering the parentheses x minus 2 as my new factor that is my greatest common factor between the 2 terms. So if the new greatest common factor is x minus 2, then from the first term I am left over with x squared, and from the last term I'm left over with positive 16. And that is all you have to do to factor by grouping. Make sure you always check and see if any of those 2 new parentheses can be factored any further. Now let's consider the second example we have here. And we're going to break up the problem into 2 parts again because there's no greatest common factor that they all have. So the first 2 terms have their greatest common factor as 2m squared. And the leftover, and what's left over from the 2 terms is 3m minus 1. Now looking at the second 2 terms, we should notice immediately that this new lead coefficient starts with a negative, therefore we have to factor out a negative. Now if we look further and we try to come up with other numbers or variables that these 2 terms of negative 3m and 1 have in common, it might seem like there's nothing, but remember that 3 can be written as 3 times 1. So, and 1 is 1 times 1. So we can say that they have in common a greatest common factor is just a 1. And then we are left over with 3m minus 1 because we factored out a negative 1, not just a 1. So when there's no other greatest common factor, we would just say 1. And to finish off the problem, we just say 3m minus 1 is my new greatest common factor, and we are left over with 2m squared minus 1. And you are done. Now let's consider how we would factor when we have 3 terms, so a trinomial. And specifically at a trinomial with a lead coefficient that is not 1. And we're going to do this by using grouping besides a couple of other strategies. So the first thing you want to notice is that we're going to consider trinomials that are in this format, where a, b, and c are numbers, a is the lead coefficient, b is the coefficient for x, and c is our constant. Now, the first step you need to do is check for the greatest common factor and make sure your trinomials are in this format, that the terms are in the correct order. Then you're going to find 2 integers, and we're just going to call them m and n, that multiply to give you whatever the value of a times c is. And those 2 integers, m and n, not only have to multiply to give you a times c, but they have to add to give you whatever the value of the b is. So let's consider this first example first and foremost. So in this case, I have to multiply a and c, which is in this case 3 times 4, so 12, and I need them to add to 13, so which is b. So what two numbers add to 12 but multiply to 13? And the work I'm showing right now is not necessary. I'm just going to talk you through how to consider this. So a couple of numbers that multiply to give us 12 is 2 times 6, 3 times 4, and of course 1 times 12. Now I actually made a mistake and I lost the negative from the 13, so I need to be careful because that makes it important. Because what kind of two numbers multiply to positive but add to a negative? So they would both need to be negative numbers. And the correct numbers that work that multiply to give us 12 but add to give us negative 13 are negative 1 and negative 12, so that is my m and n. Now, what do we do with these terms once we have them? What we're going to do is keep the first term with the lead coefficient and the constant term of 4. But what we're going to do to finish this off is we're going to take those two new integers and replace this negative 13 with negative 1 and negative 12. But that negative 13 had b as its variable, so we're going to add b to each of those new integers. So if you look, if I were to combine these two terms back and negative 1b, negative 12b, that would just give me the negative 13b that we originally started with. And the reason we like doing this is because now we have 4 terms and we can factor by grouping. So why don't you practice factoring by grouping? Now this next problem might not look like it is in the same format as this one because the exponents seem a little off. I'm going to quickly show you why that's not the case, but we're going to just solve it the same way as the other one, and I'm going to show you why we can do that. So let's say that I let m equals x squared. Then I could replace this x squared with an m, and I would have 7m plus 6, and then x to the fourth, well, x to the fourth is just x squared squared, right? So I could say x squared is m, right? So instead of x squared, I can just say m squared plus 7m. So as you see, this is just a more complicated way to have this problem written where 2m squared plus 7m plus 6, where m is equals to x squared. Just write it in its more simpler format. So since replacing these variables with another one that defines m as x squared still keeps us in the same format as what we were originally given, we can solve this problem as before without having to replace m with x squared. Now you could continue solving this problem as we did the one on the left, and then at the end replacing m squared with m with x squared. However, I'm going to show you a quicker, shorter way, as long as you recognize a problem like this can be solved by factoring this way. So just as before, I'm going to consider what AC in this problem is. So it is, again, 12, and what B is in this case, which is 7. And we've already considered all the factors that give us 12, and the ones that would add to 7 from the left side are 3 and 4. Right, because they add up to 7. So all I'm now going to do is replace the 7 with 3 and 4, but since 7 had x squared with it, we're just going to add x squared to each of these terms. They were both positive, so I'm going to keep them positive, and I'm going to add my lead term as well as my constant. And now it is again 4 terms, and I can factor by grouping. So give this another practice. And our final answer should be 2x squared plus 3 times x squared plus 2, and none of those factor further, so we are done. And we're going to now practice other types of factoring. Now we're going to consider how to factor trinomials with the lead coefficient of 1. Let's try factoring this type of trinomial the same way as we did before. So we would consider what two numbers multiply to give us negative 30, and what two numbers that multiply to negative 30 add to negative 1. And that is just going to be, well, to multiply to a negative number, I have to have one positive and one negative. So the two numbers that come to mind are 5 and 6. And one of them needs to be negative. So I'm going to make 6 negative so that they add to negative 1. Now, when I replace the middle term, I can write them in any of the order. I can write it as 5 first or negative 6 first. So that doesn't matter, but I will replace this negative x with this. So I'm going to have 5x minus 6x and keep my lead term constant. Now again, I could have written those two terms in any order, but now let's factor by grouping. Notice not only did the last two terms have a negative in common, but again, the negative lead coefficient in the second group made me factor out a negative. So our final answer is x plus 5 and x minus 6. So you can still do problems with the lead coefficient of 1 the same way as before, but hopefully you notice that there's a shortcut that if you want and choose to use, you can. Our original two numbers that we got were 5 and negative 6, and as you notice, you can simply, once you get the two numbers, when your lead coefficient is 1, you can simply just write them as x plus the number or minus the number in your two parentheses. So let's look at the other two problems we are given here. Now this first problem, the first thing we need to do is reorder it so that it is from highest to lowest exponent. Now hopefully as soon as you do this, you notice that our lead coefficient is negative. So we definitely have to factor that out, but also don't forget to check for GCF, and in this case it is y. So let's factor out the negative as well as the greatest common factor. Now again, I strongly recommend that you, when you factor out a negative, that you double check all of your signs are correct, which in this case they are. So after you factor out a GCF, you always want to look inside the parentheses and see if that can be factored further, which in this case it can be. So what two numbers multiply to give us negative and add to negative 3? And the two integers that work are negative 4 and 1, and since there is no lead coefficient, I can just write this problem as y minus 4 and y plus 1 and put my greatest common factor out front, and we are finished. Now when considering the last problem, we have the same type of exponents as we did in the previous slide, where we have 4, 2, and no exponent in the last term. So we hopefully know that I'm just going to have y squared and another y squared in each of the parentheses. Since there's no lead coefficient, I just need to figure out what two numbers multiply to 21 and add to 10, and that's just 7 and 3, and they're both positive, and you are finished. That's how easy it can be. Now, if you are ever given two terms, you have to decide, is it a difference of two perfect squares or not? If it is, you can use the following formula to factor. And the reason this works is here. If I was to FOIL that back, I would get the work below, and the middle two terms would simplify, which would give us the original, which is why we can say when a squared minus b squared, it's just a plus b, a minus b. This first problem has a greatest common factor of 3, so we have to factor that out, and then we're left with w squared minus 25m squared. If you look, as I've said, you always must check out the parentheses and see if you can factor anything further. Now we have w squared and 25m squared, and 25 is just 5 squared. So we can write this parentheses as w minus 5m and w plus 5m. And don't forget the GCF, and we are done. Now with the next problem, we should first write it in order, so negative x squared plus 4, and then since it starts with the lead coefficient that is negative, we have to factor that out, so it is negative parentheses x squared minus 4. Now that we have done this, we can notice that it is a difference of perfect squares in parentheses, and my final answer is negative x minus 2 and x plus 2, and that is it. The last problem might look like it's not a difference of perfect squares, but remember, just as before, m to the fourth can be written as m squared squared minus, and 16 is just 4 squared. So it is still a difference of perfect squares. So we would have m squared minus 4 and m squared plus 4. Now, the most common mistake is that you will stop here. But if you look, this parentheses is still a difference of perfect squares. So we must continue and factor completely. So what we would have here is m minus 2, m plus 2, and we still have our original second parentheses, which is m squared plus 4. And since that is a sum of perfect squares, we are done factoring. Now, what if we have a difference or sum of two perfect cubes? So this will still be two terms, but they'll be cubes instead of squares, and we can do the following formula with differences and sums. So we have a little acronyms we like to use to help us remember how to factor a difference or sum of two perfect squares, and that is crummy, crummy, SOPs. The crummy helps us remember what to do for the first factor, and the SOPs helps us remember what to do for the second factor. So the first parentheses you get by cube rooting each of the terms. Now, in this parentheses, you're always going to keep the original sign between the two new terms. Your second parentheses comes from the acronym part that says SOPs. The S stands for the square of one of the terms we've just created in the first parentheses. So the first S stands for the square of the first term, while the last S is the square of the second term. That square we always add. Both of these squares should always be positive because when we square something, it's always positive. Now, there's going to be a third term that goes in the middle of the second parentheses, and that's where the O and P come from. So OP stands for opposite product. And when we say opposite, it just means it's going to have the opposite sign of the original sign. And the product is just the product of the two terms we are squaring in this parentheses. So let's look at an example. So in this first problem, we have to factor out the greatest common factor of 2 first. And then I look at the parentheses and I can immediately tell that I'm going to be working with potentially cubes. And since w to the third is a cube and 27 is also a cube of 3. So I can use this formula to factor with crummy SOPs. So what am I cubing? I'm cubing w and I'm cubing 3 and I am adding them together. So that's in essence going to give me my first parentheses. So my first parentheses is crummy, so cube root of w to the third, so that's just w. And then cube root of 27, which is just 3. And I'm going to keep my original sign. So that's crummy. Now SOPs just means I'm going to square my first term, so that's w squared. And I'm also going to square my second term, and I know that's going to be positive. And then I'm also going to do the opposite product, SOPs, opposite product. So opposite, instead of positive, I'm going to have negative, and product is just 3 times w. And I just need to simplify that 3 squared, and I'm done. But don't forget the greatest common factor at the beginning, and the second parentheses cannot be factored any further, and you are finished. Let's try the problem on the right. First, we must rearrange it and factor out any greatest common factor. There's no greatest common factor, but there is a negative lead coefficient, so let's factor that out. In the parentheses, we have a difference of perfect cubes, so my first parentheses should be cube root of x cubed, which is x. Keep the same sign, cube root of 125, which is 5. So that's crummy. I still have the negative up front as my lead coefficient, and now I'm going to do the SOPs. So square of the first term, that's going to be squared of x, so x squared. Opposite product, I started out with a negative, so I'm going to have positive. Product of x times 5 is just 5x. And then the last term is always positive because I'm squaring the second term. So squaring the second term is going to be 25. And that is it. This is all we need to know for factoring. Now let's go practice.